Bhubaneswar flow, and you see that the survival probability has dropped to 1/3. Okay, SK, the survival probability, the elastic scattering ratio measured was 46%, but the survival probability is 36%. That is what we said the correction for the neutral current correction. You see, 36% has remained nu E, so 64% has gone into nu mu. But you see that with a 1/6 the detection efficiency, so that 60% becomes 10% when you add the two you get 1. Yeah? And snow can see neutral current, okay, so and then you get, okay. So you see the low energy neutrino survival probability is little more than 50%, whereas all the high energy neutrino survival probability is about 1/3. Okay, so we have to understand both the magnitude of the survival probability as well as energy dependence of the survival probability. For that, we have to discuss the matter enhancement of solar neutrino solution, the so-called resonant conversion or MSW effect, after its authors Mikhail, Smirnov and Uldenstein. You see, sun has a density of electron is very high. So nu E interact with electron, okay, to have charge current interaction, so shown here, okay. So we have to consider the potential, the interaction potential energy coming from that reaction. And in the last class, we had said that is parameterized by the simple Fermi coupling constant here, and times the electron density of the conformation. Okay. What we had discussed yesterday as the plane wave solution, okay, was the solution to the free particle Schrodinger equation, okay, d over dt is equal to energy which is momentum plus m square of 2e time. Okay. So that is the free particle Schrodinger equation. Okay. What I have written as psi 1 2 is a shorthand for u1. Okay. So we have to add to that. So that is the kinetic energy. To that we have to add the potential energy. Now this potential energy, this is affecting only nu E, not nu mu. Of course, there is a neutral current, but neutral current is common to all these spaces, so it has no negative. Can ignore it. Okay. So to take that into account, we have to go from the mass basis to the flavor basis. Okay. So this we have to replace by nu E nu mu times cosine theta sin theta factor of this whole. Clear? Okay. So we have to do this and put that cosine theta sin theta factor. And left hand side also we have to put that cosine theta sin theta factor. If you go from nu1 nu2 to nu mu, and that cosine theta sin theta factor you can take to the right hand side on the inverse. So you get the three particle Schrodinger equation in the flavor basis, but m square is not simply m1 square m2 square, but it is multiplied by the sin theta cosine theta factor. Okay. So sin theta cosine theta factor is coming from here. Okay. And on the other side it is coming from. Clear? To that we have to add this potential energy term. So our mass, the mass matrix we had, m square, okay, also has a potential energy contribution. So this was the mass matrix. To this we add this. Okay. Root 2 G8 Ne was the potential energy, okay, we get a effective matrix for mass or energy. Okay, this one, the nu e part is this. These are the off-diagonal terms, and nu e part is this. Okay, nu e part has got this extra contribution from interaction dissonance. So the program reduces to finding the eigenvalues and eigenstates of this, effective mass or energy. But we can simplify it further if we assume for a moment that sin theta is small. It's not correct and it's not necessary. You shall see in a moment it's not necessary. But let us start with that to make the discussion simple. If sin theta is small, then that means this sin theta cosine theta, SC stands for sin theta cosine theta. That means the non-diagonal elements are small. Okay? So you can identify approximately each diagonal element with an energy eigenvalue. So this diagonal element with one eigenvalue, this diagonal element with one eigenvalue. And the corresponding eigenstates mu1 and mu2. Okay, this is mu1 and this is mu2. You can identify with the clever eigenstates mu me and mu. Okay? So let us assume that mu, that is this eigenvalue, which is dominantly M2 because angle is assumed to be small, has a larger mass than mu1, which is associated with the electron. Okay, but as we go inside the sun, this one does not get any potential energy contribution, so this remains constant. Okay, okay. Now the first eigenvalue, that increases steadily because electron density increases as you go inside the sun. Okay, so there is a crossover. Okay, and that crossover electron density is given by when these two diagonal elements becomes equal, and this is very easy to see. It is delta m square cosine 2 theta over 2 into root 2 gf times energy. Okay, but mind you, there is a finite gap. If they don't actually cross over, there is a finite gap that is given by the twice the off-diagonal element, so delta m square sine 2 theta. Okay, okay. It is very easy to see because trace remain invariant under diagonalization. Okay, so A plus B, and the determinant remains invariant. Okay, so that is AB, Okay, so A plus B whole square minus 4AB gives you A minus B whole square. Okay, so the two diagonal elements. So there will always be finite gap, and you can calculate that gap. Okay, A minus B. This is given by the off-diagonal. Okay. So let us try to see what is happening. You are producing nu e, which because assumption of small mixing angle is dominantly mu1 with eigenvalue lambda 1. It is coming down and it is going out as mu2. So nu e producing at the solar core is escaping as mu. So the survival probability is sin square theta. Because mu2 has mu e component which is sin theta. If you assume adiabatic condition, that means there is no transition between one eigenstate to the other eigenstate. Okay. Now, this assumption of small mixing angle is totally redundant. We don't have to make that assumption. Why? Because what we are concerned is not the mixing angle in vacuum, but the mixing angle in matter. Okay? And this tan 2s of that mixing angle in matter is given by twice the off-diagonal element over the difference of the two diagonal elements. That is the angle which will rotate it into a diagonal matrix. Okay? So sin square 2 theta, if you take the difference of the two diagonal elements, you see is cosine 2 theta minus 2 gf. Okay? So if you are at the solar surface, where the electron density is 0, okay, then of course it gives you the vacuum mixing angle. But when you go to the crossover point, then you see that the denominator, these two terms cancel, so denominator varies, okay, okay. So tan 2 theta becomes infinity, so 45-degree maximal mixing, that is called resonant conversion, okay. But when you go to the solar core where neutrinos are produced, then that density is much bigger than the crossover density. So the second term is much bigger than the first term, okay. So tan 2 theta matter at the core will always be small, no matter what it is in vacuum, okay. So what is happening? So nu E that is produced in the solar core is traveling as nu1, okay, irrespective of the vacuum mixing angle, okay. And when it's coming to the crossover point, okay, there you have resonant conversion, 45-degree mixing angle, whatever be the mixing angle, okay. And by the time it comes out as nu2, which has a nu E component given by sin theta. So sin theta, be it small or large, it will come, the survival probability of solar neutrino on Earth will be sin square theta, okay, okay, provided core density is more than the crossover density, and there is no transition between these two. That is called the adiabatic condition, okay. Adiabatic condition comes from a calculation by Landau and Jenner going back to the 1930s, which were done in a different context. But the essential point is the transition rate is e to the power minus pi over twice gamma, where gamma gives the ratio of change of the first eigenvalue over one oscillation wavelength relative to the gap between the two eigenvalues, okay. And the rate of change of the eigenvalue will be proportional to rate of change of the electron density, okay, because the change because the eigenvalue is changing because of the electron density, okay. So that means that if the electron density gradient is so small that the resulting change in the eigenvalue over one oscillation wavelength at the critical point and the crossover point is much smaller than the gap between the two, okay, then of course gamma will be small, so this will be exponentially suppressed, okay. So there will be no transition, okay. So if these two conditions are satisfied, the nu E will emerge as nu2, okay, with survival probability sin square theta. The left condition means that the core density of the sun is more than the critical density, and right condition ensures that there is no adiabatic condition, no transition, okay. So if these two conditions are satisfied, that gives you this triangle in the sin square 2 theta delta m square log plot, and this is called the MSW triangle, okay. Again the point is very simple. Sin square theta be it 10 to the minus 3, minus 2, minus 1 doesn't matter, cos 2 theta will be always merely 1, okay. So delta m square, okay, say E as 1 MeV because the solar range 1 MeV comes in the middle, okay. So take it 1 MeV. So the delta m square should be less than 1 MeV times Gh, and solar core density, electron density, no, we put that value. You see that the value of delta m square is 0.5, so it will be below that line, okay. But there is a lower limit of sin square 2 theta, which is 10 to the power minus 3. You see from here. Why? Because that will the gradient here, the density gradient, again you take from the standard solar model of Bakali, so that gives you density gradient. That tells you that it will be consistent. Okay? And it is a log plot. So the limit is on the product delta m square sin square 2 theta. In a log plot, it will be a sum log delta m square and log. So it will be a plus b constant, okay, x plus y constant. So it will be diagonal line. Okay, draw the diagonal line. So if you are going by 3 orders of magnitude here, and here it will go by 3 orders of magnitude. So this will be the triangle. Clear? Now, if you are inside the triangle, then suppression is sin square theta. So sin square theta can be 1/3. Okay, that the high energy expression. See? If you are outside the triangle, then the suppression is that average suppression we have to say 1 minus half sin square 2 theta, which you have seen earlier. Okay? Okay? So that can be larger than 50%. So you have two solutions, large mixing angle solution, small mixing angle solution. What happens? You see, the PP neutrino less than 1 MeV, which is dominating gallium experiment, okay? Okay? You see, the energy is here scales with mass, so that will be, for that you will become above the triangle. But the high energy experiment, boron neutrino more than 5 MeV, that takes you inside the triangle, okay? So you get sin square theta for the high energy neutrino suppression, you get 1 minus half sin square theta for the lower. Okay. So, okay? Here you have similar thing, except they can be distinguished with energy dependence. You see, here it is monotonically going from more than 50% to 1/3, okay, and staying at 1/3. Okay. Here, sin square theta is very small, so it is 1 here. It becomes 0 here. It again becomes 1 here. So it's a very rapid and non-monotonic energy dependence. Okay. Finally, there would be vacuum solution. In this case, there would be vacuum oscillation, which gives you lower antinodes. Okay. Again, a rapidly energy dependent. Okay. And there is one fourth solution called low solution. It comes because the following reason. You see, in the night time, the solar neutrinos are passing through Earth. Okay. So, in that process, there is a regeneration of nu E from nu. Okay, and that quantity is always positive, very small but always positive. So it is said the sun shines a little brighter at night in the nu E. Okay, but and it is concentrated in this region. Okay, okay. So in this solution, low energy gallium experiment, okay, takes you up there. And that is a radiochemical experiment, so you are collecting over a month, there is day contribution, night contribution. Okay? So that night contribution will give you that extra, otherwise it will be sin square theta. Okay? So these are the four solutions you see from the rays which have to be distinguished by energy dependence of the factor. Okay? You see, energy dependence. This is the vacuum, the small mixing angle solution. Okay, we shall go from 1 to 0 and back to 1. Okay. The rapid energy dependence, this is the vacuum oscillation solution. Okay. Whereas the large mixing angle is that going from 0.55 to something like 0.3. This is the best solution. Okay. The low solution takes from 0.55 to 0.45 because it's the small earth matter effect, cannot take it. Now what happened? The SK gave you the energy dependence and you showed from 5 to 14 MeV within 25 plus minus 25% in 0.45. So, okay, actually plus minus 10%. So it remains between 0.4 and 0.5. So within 20%. Okay. So there is no way that the small mixing solution or vacuum solution will be compatible. So that energy dependence, so measuring energy dependence is important. So that energy dependence is ruled out. You see, low solution has survived because if you remember, there was a 20% uncertainty in the Bakhal's estimate of the boron neutrino flux. Okay? So the low energy fellows is the